by x squared minus 4x and then plus 3. Okay, and the graph will look like this. Let's just copy from my note. I use red color then. Graph will be like this. Make sure that I copy it right. I'm going to zoom in a little so make it look better than what I see in my calculator. It's going to be like this. Okay. And then the middle part going to be like this. And then the last part going to be like this. Okay. This is 1 right here. This is 3 right there. So you see that there are 3 curves in this graph. All right. And you see that the graph is getting closer and closer to the vertical line, x equal to 1, x equal to 3, but never intersect. Okay? And that's why you see in here that we also have a horizontal asymptote as well at the x-axis. Y equal to 0. The graph is getting closer to the x-axis when x equal to positive infinity or negative infinity. But we'll talk about that later. For now, we're focusing on the vertical asymptote. And you have 2. And see right here, one more time, it convinces you what? If you have the domain, you see, x cannot be equal to 1, x cannot be equal to 3, then you have 2 vertical asymptotes. Okay? X equal to 1, x equal to 3. Now, let me show you some exception, some special cases that may not be that way. Show you this. F of x, another example, the third one, equal to 3x plus 6 over, how about x squared plus x minus 2, I think. Okay? So, how do we find the domain and how we find the vertical asymptote? Let's factor this out again. If I factor the denominator out, I got what? X plus 2 times x minus 1 on the bottom. On the top is 3x plus 6. Okay? So the domain is what? All real numbers x except for negative 2 and except for 1. So x can be anything. Gotta be different from negative 2, different from 1. And the reason we explained before, when negative 2 is a 0 of denominator, make denominator equal 0. And it's not good when you divide by 0, right? So x cannot be equal to negative 2, x cannot be equal to 1. And you should expect, and you are expecting that we have 2 vertical asymptotes, x equal to negative 2 and x equal to 1. However, I claim that in this case you only have 1 vertical asymptote, not 2. Why? Let's factor out the numerator, see what happened in here. So instead of writing 3x plus 6, I'm going to write this way, 3 times x plus 2. Okay, 3x and then 3 times 2 is 6, right? You see what's so special on this example right here? The numerator and the denominator have a common factor, which is x plus 2. So in order to find a vertical asymptote, you really have to cancel out the common factor. Okay, this one. And as a result, you only have 1 vertical asymptote of x equal to 1. Alright, so x equal to negative 2 is not going to be a vertical asymptote. And the graph of this one is going to be like this. It's kind of similar to the graph of 3 over x minus 1, except for 1 point different. Okay, see, when you cancel out x plus 2, so 3 over x minus 1. And then, of course, the vertical asymptote is x equal to 1. Green color again, x equal to 1 is right here. Right. Make it longer. X-axis right here, y-axis right here, and let me use red color. And the graph going to be this. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 over x minus 1 plus 3 over x minus 1. 1 Okay, the origin is a 0 right here. The line right here is at x equal to 1. If you look at the graph right here, you see what the domain of this function is what? All real numbers from negative infinity up to 1, and then from 1 to infinity, except for 1, right? So all real numbers except for 1. This is a graph for 3 over x minus 1. However, in our real function right here, actual function right here, the domain is what? All real numbers except for negative 2 and 1. So what's wrong with negative 2? So negative 1 right here, negative 2 right here. This is the graph of this one. And I claim this our real graph right here, actual graph right here, very similar to this, except for one point. At negative 2. At the point right here, negative 2. It's just missing the point. Okay, let's make a hole right here. Now it makes sense for everything. The domain of this one is what? All real numbers except for negative 2 and except for 1. Okay? Because for this function, we cancel out a factor. We don't accept x equal to negative 2. For this function right here, we are okay with x equal to negative 2. That is the only difference. So for this graph, instead of having the vertical asymptote with x equal to negative 2, we say like there's a hole at x equal to negative 2. Okay? That's a hole right here. So we're just missing a point right there. That's all we're saying. So for graph of rational function, whenever you have a common factor between the numerator and denominator, and you sketch the graph, you're going to have a hole at that value of x. Okay? At that point. And as a result, you have one less vertical asymptote. Okay. Let me move on to the horizontal asymptote. Right? Number 2, horizontal asymptote. Number 3. Horizontal asymptote. And I will denote it by HA, the horizontal asymptote. Okay? The key to find the horizontal asymptote is, for now, okay? When we count 1, it's going to make sense everything. You're going to use limit. But for now, it's just write this way in the informal language. It's help you to learn. You guys going to compare the degree of the numerator, so the degree of p of x, to the degree of the denominator, q of x. Okay? We have 3 cases. First one, if the degree of the numerator is less than the degree of the denominator. In other words, the fraction is proper. Then you will always have a horizontal asymptote as y equal to 0, which is the x-axis, always. Always. So example, we use the same example that we had before, that you see it already, f of x equal to 3 over x plus 2, right? The top is degree 0, the bottom is degree 1, because degree 0 is smaller than degree 1. You've seen the graph already. Let's get it small right here. See what? The graph is getting closer to the x-axis, right? But never intersect horizontal asymptotes. Y equal to 0. It doesn't matter how small the asymptote you got, the degree of the top is less than the degree of the bottom. You automatically have the x-axis as your horizontal asymptote, for sure. Okay, second case. What if they have the same degree? Degree of p of x equal to the degree of q of x. Okay, so how do we find the horizontal asymptote? The horizontal asymptote is going to be y equal to the leading coefficient of p of x over the leading coefficient of q of x. In other words, you're taking the ratios of the leading coefficient of the numerator over the denominator. So example, I have f of x. Keep in mind, this time I only talk about the horizontal asymptote, okay? So I got what? F of x equal to 4x minus 1 over 2x plus 3. So you see rational function right here. The top, the numerator, is a polynomial of degree 1. the bottom, the denominator, is a polynomial degree 1 as well. So the same degree, 1 for the top and the bottom. And you want to find the horizontal asymptote? We write what? Y equal to, leading coefficient for the top is 4, and leading coefficient for the bottom is 2, so it's y equal to 2. That's the horizontal asymptote. Okay. And if you want to sketch the graph of that thing, it's going to look like this. It's x-axis right here, the y-axis right here, and for this one, the horizontal, the vertical asymptote is -3/2, so -1/2. So here, x equal -3/2. After the 2 out like that, it's for the bottom, 0 for the bottom. And the horizontal asymptote is at y equal to 2 right here. Y equal to 2. Okay. Okay. And the graph of this thing gonna be like this. What color am I using? I need another one. How about blue? Okay. Graph gonna be like this. Say x equal to 0. I got -1/3, so the graph gonna be like this. Okay. It's getting closer to the horizontal asymptote, getting closer to the vertical asymptote, but never intersect. Okay. Let me double check to make sure that it's right. X equal to y equal to 2, yeah, equal to 10. Let me double check for the graph, okay? Make sure that what I show you is correct. If it's wrong, then I'll fix it. X equal to 4x minus 1 over 2x plus 3. Beautiful. Yes, looks right. Okay. Now let's we talk about the case where the degree of the top and the degree of the bottom is equal. Then you find the horizontal asymptote by taking the ratio of the coefficient. All right. The third case. What if the degree of the top is bigger than the degree of the bottom? Okay. Case number 3. Degree of P of x is bigger than the degree of Q of x, then you will have no horizontal asymptote. All right. So we cover the case that we have horizontal asymptote. We can only have horizontal asymptote whenever the degree of the numerator is less than or equal to the degree of the denominator. If it's less than the x-axis, will be the horizontal asymptote. If same degree for the top and the bottom, keep in mind this case, the fraction is improper already, okay? Then you find the horizontal asymptote by taking the ratio of the leading coefficients of the numerator over the denominator. And of course, the third case is no horizontal asymptote when you have degree of top is bigger than the degree of bottom. Okay? Then no horizontal asymptote. Let's move on. Okay, so number 4 right here, oblique asymptote. Abbreviated by OA then. O for oblique and A for asymptote. You can only have an oblique asymptote whenever the degree of the numerator is exactly 1 bigger than the degree of the denominator. In other words, the degree of P of x equal to the degree of Q of x plus 1. So degree of the bottom plus 1 equal to the degree of top, or degree of top is 1 more than the degree of bottom. Then you have the oblique asymptote. And then the oblique asymptote can be calculated by doing the long division and equal to what? The quotient, I think. Quotient of long division. Okay, so I think it's a good chance for me to recall or review long division for you, or a shortcut of long division, because synthetic division is help you to find the oblique asymptote. Right? Let me give you an example. Say f of x is equal to 2x squared minus 3x plus 5 over, say, x minus 2. Okay? We just talked about the oblique asymptote in here. Look at this rational function. The top is polynomial degree 2. The bottom is polynomial degree 1. So 2 over 1 right here. 2 is 1 bigger than 1. Okay? You know they have the oblique asymptote. And we can do the long division here to find the oblique asymptote. You take the numerator divided by the denominator. Should be that way, right? That's x minus 2 here. Then 2x squared minus 3x plus 5. Oop. That's how I write it. 2x squared minus 3x plus 5, you write down here. Okay? And you're going to do a long division. 2x squared divided by x. 2x squared over x is equal to 2x. You're going to write 2x up here, and then multiply the back. 2x times x is 2x squared. 2x times negative 2 is negative 4x. Now you do a subtraction. 2x squared minus 2x squared is 0. Now be careful with this calculation right here. Negative 3x minus negative 4x. Let me write down here. Negative 3x subtract negative 4x. Because what? This is positive x. Okay? Because this is negative 3x plus 4x. This is x. And you drop the 5 down, plus 5. Okay? Now repeat the procedure. Take x divided by x. You've got 1, positive 1. So 1 times x is x. 1 times negative 2 is negative 2. And you do subtraction one more time. X minus x is 0. Now what? 5 minus negative 2 is 7. And this got the remainder right here. What we care about is the quotient. This is the quotient. And you know what? The oblique asymptote is y equal to the quotient. So y equal to 2x plus 1, right? This is a line, you see? Slope is 2, y-intercept is 1. The oblique asymptote. Let me show you the graph of that function. X, y-axis, x-axis, y-axis. You see that we have a vertical asymptote of x equal to 2. X equal to 2 is right here. You have a vertical asymptote. And the oblique asymptote is 2x plus 1. It's going to be like this. Okay? And then the graph is going to be like this. Red color then. I have to draw it better. Okay. So it's getting closer and closer to the two asymptotes, but never intersects. Okay. There is another way of doing long divisions called a synthetic division. And synthetic division, I claim, is faster. However, it's a very limited use. You can only apply synthetic division if the denominator, the divisor right here, is of the form of a single x plus or minus a number. If it's not the case, then you really have to go over the whole long division as I'll show you right here. Okay. In synthetic division, another way to do long division, short way called synthetic division. And I claim it only works if the divisor is of the form x plus a number k. Okay? So I'll give you an example right here. It's actually match up with the case that we're talking about. The divisor right here is of the form what? X plus -2, right? Plus a number. Then we can do synthetic division. For those who learned this already, shouldn't be surprised, but if first time seeing it, this is how we do it. We're going to write the opposite of -2, or the zero denominator, which is 2 right here. And we're going to list out all the coefficients for the numerator, which are 2, -3, and 5. Oh, by the way, if you have a missing term, you should write a 0. If you got something like this, 2x squared plus 5 divided by x minus 2. You see what? We are missing the x term, right? Square and then number. And you should write this way. 2 for the 0 denominator, and then 2, 0, and 5 for the dividend, okay? The coefficient for the numerator, okay? You missed the 0 right here for the x term, you won't be able to do the synthetic division correctly. So be very careful with that. In this example, I don't have any 0 terms, so I listed them all out. Okay? Now, this is what we're going to do. We drop the 2 down, okay? Drop the 2 down. Then 2 times 2 right here, we take 2 times 2, you got 4. And you're going to write the 4 right underneath the next coefficient. -3 plus 4, we got 1 right here, and repeat the procedure. And then 1 times 2 is 2, take 2 plus 5, you got 7. No more, you stop. This number right here is your remainder. And those two numbers right here will be the coefficient for the quotient. And you understand this as 2x plus 1. And this is the quotient. And of course, you guys can have the same answer as you do long division. One more time, this synthetic division is going to be faster. But it has limited application. You can only use synthetic division if the denominator or the divisor right here is of the form what? A single x plus a constant. Okay? Otherwise, you have to use a full version of long division as I showed you a minute ago. Alright? And that is how you find the oblique asymptote by looking for the quotient of long division. Alright? And this is the end of section 5.3. It's also the end of our video clip today. Thank you for watching, everyone. Should you have any question, please email us and I'll try to reply to you as soon as I can. Thank you so much and have a good day.